Okay, here we go. All right, so just, I guess, a couple things to point out on this warm up here. Um, so you're trying to find the proportion. It says here that they talked to people and they found that 60% of us spent less than 7,500. So that's the p hat right there. Use a 0.05 level of significance to test the claim that less than 62% of brides spend less than 750. So we want to, that's what they're claiming about the population. So that's why that's my P. So my null says they're equal, alternative says less than 0.62. So the proportion of brides who spend less, and P is the true proportion of brides who spend less than 750. All right, so this is a one sample z-test for proportions. Random, so yes, it's stated that they took a random sample. This is, I think I changed here to say randomly selected. The normal check, so again, you're using P here. Both of those are at least 10. We have to assume that there's at least 25,000 brides. You can do it the old way, or you can do it the new way with the calculator. Your p-value is less than, I picked a significance level here, so your p-value is less than alpha, reject the null. There is enough evidence to conclude the proportion of brides who spend less than 7,500 is less than 62%. So if I used a 0.01 level of significance, my p-value would be greater than alpha. So then I would fail to reject, and I would not have enough evidence to conclude the proportion of brides who spend less than 750 is less than 62%. If my HA had a not equal in it, this number would still be the same, but my p-value would change because my p-value would have to be now in both tails. So I would double that original one and come up with this number, but this number is still going to be less than my alpha of 0.05, so the conclusion would not change still. I'd still reject Joe. Okay? All right. So today we're just talking about how to do these tests with the mean. If you remember when we did confidence intervals, we used Z for means if we know sigma. I remember sigma is the or SX, whatever, is the population standard deviation. We use T for means when sigma is unknown, but we know SX, okay? We did like one example back in chapter 8, but then we kind of realized that this really wasn't, using Z really wasn't realistic, because if we were trying to estimate the mean, we wouldn't know the population standard deviation. So we pretty much use T all the time. So in this chapter, we're just going to use T. We're not even going to use it. It's not that it's not possible. It can be done. It's just that your book doesn't focus on it, okay? So when we write out our hypotheses, so if we're testing, we're testing the mean today. So mu, so you'd have HO, mu is equal to HA, mu is greater than, mu is less than, mu is not equal to. And again, you want to define mu, so the true mean, blah, 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 blah. If you need to, pick a significance level here. All right, your method. So it's a one sample t-test for means. The random check we want to check, or is it from an experiment with random assignment? All right, the normal check. So remember, for means, it's different. Either your population is normal, your sample size is greater than or equal to 30, which is your central limit theorem, or you can look at a graph. And remember, we did this last chapter. You're just looking for no skew, no strong skew or outliers. Then the observations independent are from an, if the observations are from an experiment with random assignment, then they'll just be independent. If the observations are from a sample taken without replacement, then you're going to check that 10% condition. All right, your test statistic. So it's the value, in this case the sample mean, minus the parameter, so statistic minus the parameter, which in this case is mu, divided by the standard deviation of the statistic. Back in chapter 7, we said the standard deviation of x bar was sigma over the square root of n. But we don't know what sigma is, so we're using the standard error when we plug in Sx. On your calculator, this is option number 2, t-test. To find the p-value, it's t-CDF, and the degrees of freedom are n minus 1. All right, this right here looks the same as it's always looked. So if you're given a significance level, compare your p-value to alpha. If not, make sure you choose one in step 1, compare it here. Are you going to reject or fail to reject? And then write your final piece in reference to HA. So you have enough evidence to conclude, or there's not enough evidence to conclude. It looks the same, okay? I'm not changing anything there. All right, this next one right here. We'll do this next one together, and then I'll show you the last one. All right, so the studio claims to play an average of 50 minutes every hour. However, every time you turn the station on, it seems like there's a commercial playing. To investigate their claim, you randomly select 12 different hours during the next week and record what the radio station plays in each of the 12 hours. Here are the number of minutes of music in each of these hours. Carry out a significance test of the company's claim that it plays an average of at least 50 minutes of music per hour. Test at the 0.05 level. Significance, follow the 4 steps. All right, when it says at least 50 minutes, so at least 50 minutes would be greater than or equal to 50. There's an equal sign in there. So my HA is testing that it's less than 50. That's what I'm trying to prove here. So I want to find evidence that the mean is less than 50. This is the true mean minutes of music per hour. All right, I don't know the population standard deviation, so I'm doing a one sample t-test for means. Random. Stated. All right, normal. Doesn't say anything about the population being normal. It also, we don't have a sample bigger than 30, so I'm going to have to look at a graph here. So I'm going to type in my values. I'm just going to check to make sure here that I have the right values. Yes, I'm good. Okay, so I'm going to type in my values. I'm going to look at a graph. Remember, we could look at a histogram. Okay, this is a little bit suspicious, but remember with histograms, you can always kind of adjust things by changing that X scale. So maybe it's not so bad. You can look at a box plot. So a little bit of skew here, but no outliers. Or you can look at the normal probability plot. Like I said, a little bit of a tick here and tick here, but overall, the question is, again, is there anything here that makes me think that the population might not be normal? So yes, there's something here, but I don't see anything glaring at me that's telling me the population is definitely not normal. If I look at the box plot again, I don't see any major skew. There's some, but there's not a lot of data values either. But there's nothing here that makes me think there's no way that this data is normal. All right, so I'm going to comment here just like we did last chapter. And I'm going to draw a picture there. Okay. All right, for my independent, so they did take a sample without replacement. I'm not going to write assume here because I know that there's at least 120 hours in a week. All right, again, you have two options here at this point. So option number one, go through, use the formula. So if I go to use the formula, I'm going to have to do my 1-bar stats to find what I need. So there's my X bar. There's my mu, my SX, divided by the square root of the sample size. And I think I did something wrong. That's because up here I typed it wrong. Oops. All right, that's better. All right, if I want to define my p-value, so I'm in this tail. This is the t-distribution. So I'd have TCDF, negative infinity, negative 2.567. My degrees of freedom are 11. All right, so that's one way to do it. The other way you could do it is I could go to stat test, t-test. So since I did 1-bar stats already, you could see that these things are filled in. If I wouldn't have done 1-bar stats, these things wouldn't have been filled in. So you can leave it like that and just do 50 there, and then I would select my less than. You can also go over to the data option. So I put my mu naught in there, list 1. I want the less than because that's what my AJ says. If you use the data option, you're still going to tell me what your pieces are here. So instead of giving me your inputs, you're giving me your outputs. And I'm also going to say what the degrees of freedom are, okay? All right, so then I want to write my conclusion. So they gave me a significance level up here. So the p-value is less than alpha. So if it's less than alpha, I'm going to reject HO. So there is enough evidence to say the true mean minutes of music played is less than 50 minutes. All right, what kind of mistake could we have made? So since we just chose to reject, we could have made a type 1. What does that mean in context? So we conclude the mean minutes are less than 50 minutes, but really they are not. There's a little bit more context for you. Okay? All right, so pause the video and take a second to do the next example. All right, so on this next example, you might have some issues here with this part A. So let's just go over. This number is your sample mean. This is your count. This is your SX. This is your standard error. So your SX over the square root of n. Both of these are measuring how far away is something, how far away the values from something. Standard deviation is how far away are the values from the mean. Standard error is how far are the values away from the mean of all the means. So for standard deviation, I'm just talking about that one sample. So the widths of the cubes are about 0.093 millimeters from the sample mean width on average. The standard error, I'm talking about all the x bars that I could have from all samples of size 50. And how far away are all those x bars from the mean of all them? So in random samples of size 50, the sample means are about 0.0132 millimeters from the true mean on average. Remember, the mean of all the sample means is going to be the true mean. Okay. All right, down here. The only thing I wanted you to note here, it says not, so it's a not equal. The central limit theorem applies, so don't worry about making a graph or anything like that. If you're going to do it by hand, what I did here is I found the p-value in the one side here. And then I found the p-value, and then I doubled that because that'll be both of them. You can do it using the calculator. Just type in your inputs. This is what I would see here. The p-value is greater than alpha. Failed to reject. There's not enough evidence to conclude the mean width of cubes is different from 29.5. All right, again, here's your opportunity. You pause the video, look at the problems on page 4. All right, so I'm going to go over the problems on page 4. So we're testing the mean here. And if it exceeds some value, indicate a health risk. So it's bigger than some value. So they test something and they get some x bar sample value. So your p-value is always the probability, so it's this chance of obtaining that sample value. So in this case, you could say sample mean, or something higher because we're testing if it's greater than, if the true mean cholesterol is the value considered not to be a health risk. So whatever that number is, so like, I don't know, if this is 160, so this is greater than 160. So if the true mean value is whatever that number is, 160, whatever is not the health risk, okay? This is a weird one. All right, this one right here, so they want to show greater than, so it's a upper tail, a right tail, it's on the right side. They want to show that the stand will hold over 500 pounds, so that's why we're doing right tail. We don't care about the minimum weight it's going to hold. All right. So if we commit a type 1, we reject HO, and we conclude that the stand can support more than 500 pounds, but really it doesn't. So this could be a problem because it would break. Fail to reject, so we don't reject this. So we think the stands don't hold more than 500. So we think that they're not safe, but really they are fine, okay? So like here, we probably stop the production and look at things. If they're worried about being sued for selling an unsafe product, then they need to minimize their type 1 error. So remember, your probability of your type 1 error is the same thing as your significance level. So you got to decrease your alpha then. If I want to make this smaller, then I got to make that smaller. Okay? All right, that is it for the first part of 9.3.